Okay, test. For people online, can you reply, see if you hear me or not? Okay, thank you. So good evening, let's get started. Okay, so I went a little bit of rush at the end of the previous lecture. So let's do a little bit of review, particularly the question that we did at the end of the previous lecture, okay? One of the key points that we did from previous lecture is about how do we test if a vector field is conservative field or not. So the principle we use to test this is this theory. We use a generic 3D vector field to test. Okay, so this is a 3D vector field. You can simply reduce that to a 2D, which is not a problem at all, by letting p equal to 0. To simply put it, if a vector field is conservative or not, it depends basically on this del cross f equal to 0 or not. And del cross f has a different name. We also call it the curl, which actually is what we're going to learn today. So we also write it the curl. It's the same meaning as del cross f. Now, I also want to bring it to your attention is there's a bit of a describing before this del cross f is that this vector field, okay, is on a connected and a simply connected domain, so that's okay. Now this is part here. Component function have continuous first partial derivative. That's also a condition that has to be satisfied. Okay, so sometimes if you have a function, for example, something over x squared, let's say y over 1 over x squared plus y squared, I hat, right? And then let's say another one 2 over x squared plus y here. So if you have a function like a vector function like this, 1 over x squared plus y squared, so this function will now be continuous at 0, 0, right? Then at 0, 0, then that's condition is not satisfied, okay, for the theorem. So even though if you have a del cross f equal to 0, but then the 0, 0 location will actually ruin this condition, okay? So you have to make sure that your original vector function is continuous everywhere within a certain domain, right? So that's another different condition. But of course, the major condition is del cross f equal to 0. And the other condition is it has to be continuous, right, within the domain. So that's how you check if a function vector field is a conservative or not. If it is 0, then you got a conservative field. And if you get a conservative field, then we know that, right, if f is conservative, just a color here, then and we know for sure that this vector field can be expressed as the gradient of a scalar function small f. And small f, as we call it, right? Small f is so-called potential function. Okay. So that's a condition that can be naturally derived if vector field is a conservative field. So the next question is, then how do I find this scalar function f or the potential function f? So that's the last question, last example that we have gone through in the class. Okay, so you have this vector field. First step is to verify this is a conservative field by applying that cross product, which is the curl. Okay, so you'll get that because it's a 2D field in this case, then if you look at the formula, because there's no p component and there's no z component, then the first two terms, right, they literally just going to be 0, right? If it's a 2D vector field. So you will only have one component for 2D vector field. So that's why you get only this one single component. and you have mn over there, so you can calculate their partial derivative, and they turn out to be the same. So that's why this vector field is conservative. And then the next question from here is, then what is this potential function small f then? The generic approach is listed for this 2D, and you can easily expand it to 3D vector field. So you're going to have to make use of the condition, okay? Make use of the condition. Anyway, handwriting is not working here. So you got to make use of the condition that is here, right? For the partial f over partial x to the m and partial f over partial m equal to n. Okay, so the condition is pretty natural because if f equal to del f, so that gives you m n equal to partial f partial x partial f partial y. Okay, so you have a connection established between m and n. Okay, for 2D vector field. So these are the two conditions that you will have to make use it, okay, to find what this potential function small f is. Because in this question or in this type of question, you will always have this vector field. So basically the mn, okay, these are known, right? These two are the known condition, and these two equations are also the known equations, except you just don't know what this potential function or scalar function small f is, right? So that's what you need to find out. So you can see clearly at the next couple of steps, we're making use of the two equations. First equation, we use fx equal to m. Okay, so that's the first equation here. And then for this equation, we use the simple fact that when you take derivatives back to x, you consider the y as a constant. Okay, then you're treating it like a single derivative out of here. So you integrate both sides with respect to y, right? Sorry, with respect to x. So this is what integrating both sides with respect to x, right? Integration of this side, you get this f. Integration of the other side, you're supposed to get the results, and then plus, supposed to get a plus a constant. But in this case, because of multivariable function, so we have to add an r of y at here instead of just a constant here. Okay. And when you do this integral here, you just consider y as a constant, then you get these results plus that r function, okay, y function. Once you get this step, then you plug it back into the second condition. Okay, so second condition, which is f partial y equal to n, right? That's the second condition. Okay. And plug it into the second condition here. So taking partial derivative, you get this result, and that should equal to the function n. And in this question, you're actually able to cancel, right, these two terms. You end up with just r prime y equal to 0. And then you take a derivative for any constant functions, derivative 0, and end up with a constant, right? So that's why you get r of y equal to constant. So at the end, your whole function f, or potential function f, is equal to this minus this plus a constant c. And of course, you can simply just say, okay, I'm going to let c equal to 0. You could let c equal to anything, right? And then that will be your final solution for the f. Okay, or if you keep the c, which is also good. So involving two steps at here, right? For vector function of the 2D vector function. But if you have a 3D vector function, you actually will involve in 3 steps because you have 3 conditions, right? So, but it's just exactly the same approach. Okay. This week assignments, you have plenty of opportunity to practice this type of questions, right? Yeah. So let's continue from here on the next topic, okay, which is called a curl and a green theorem. Okay. So let's talk about curl first. So first of all, let me rewrite this thing in here. Okay, so this is a curl. Okay, this is a curl we're going to talk about. This is a bigger picture. Now, if you look at the calculation of the curl, it's not really anything strange to you anymore because you already know you're simply just calculating the cross product del cross f, which is this formula over here. Right? So that's computation-wise what curl is. So it's not very difficult at all. But I think I'm going to spend a little bit of time to interpret it. What is curl and what does the physical meaning of a curl give it to us? Okay. So let's start with an example here. Okay. So let's say I have a vector field given by this function. So you have a vector field given by this function, e to the power negative y squared over 8 times I hat. So there's only one component, the g hat component 0. And if you plot this vector field out, you have a whole bunch of arrows pointing in the x-axis direction, right? Because there's no y component. And you can clearly see at y equal to 0, you have the maximum magnitude of this vector, right? And as the y goes to either negative or more positive side, the vector becomes smaller and smaller, right? So if you look at this vector field, right, it very much looks like the flow of a river, because usually the water speed is fastest in the middle and then gets slower as it's closer to the banks of the river, right? All right, so now suppose, right, you play with stakes with a dog and you throw a stake into the river. Okay, let's say you either threw it here or threw it here, and you threw it perfectly perpendicular to the river, okay, at the beginning. Okay. So what would you expect the stick to do? Or what would you expect the motion of the stick? It should rotate, right? Not only rotate, but also the stick should also flow with the river, right, with the velocity. So basically, if you threw it into the river, you would expect it to rotate. Why would you expect to rotate? Exactly, right? You feel there's a force applying to this side, force on this side here, and apparently the force on this side is a little bit bigger than this side, so that's why the stick will experience rotational motion, right, after you throw it into it. Now, this is a very, very big stick, right? Now, if you think about it, if you throw it consider it's a very, very small object or stick, then if I put it somewhere within this vector field, okay, then the motion of that little object or stick, okay, will actually give me some information about that particular location inside this vector field, right? Is it going to make a spin or is it not going to make a spin? Right. So that's the information for that particular location within the vector field is of particular interest to us. And how do we get that information mathematically? The curl. Okay, so that's what I'm going to talk a little bit about the meaning or interpretations of a curl. All right. Yeah. Okay, so first of all, okay, I had to recall some previous knowledge. So if you recall that, we have learned vector line integral. When I write this notation vector line integral, basically indicating that the curve C is a closed loop, right? So this is a vector line integral. Both ways writing are fine. And a vector line integral, if you recall, the meaning of it is called circulation, okay, of this vector field around curve C. And that's the meaning of a circulation, right? So your the F is going around this curve C, and you're doing integrals at here over the curve C, and you get a total circulation, right? So total circulation of F around the curve C. And the important portion of this formula is F dot T hat. And I have mentioned that, when you use a vector dot a unit vector, you get the length of projection of the vector, right, in that unit vector direction. And T hat at here is the unit tangent vector for the curve C. So literally what you're adding up at here, right, circulation, your F project to the unit vector direction at this moment, and you add the length of projection for the next moment. When you add up all over the curve C, you get the so-called total circulation of the F around the curve C. Okay. So now let's think about illustrate this concept a little bit more in here. Okay. I'm going to draw a very small curve C in 3D space. So when you draw a very small curve C in 3D space, if you want to describe the drawing perfectly to somebody else, then you had to give some information, right, for people to understand. For example, you said, I have a small curve C, let's say like a circle in the 3D space. Then you got to tell people that this curve C is pointing to somewhere. Because you could draw it this way, this way, this way. Because orientation is different, right? So you wanted people to understand where the small curve C is. You had to tell the people how it's oriented or what direction it's pointing to. So that information can be given, let's say, by a unit vector n hat, relative to this curve C using right-hand rule. Okay? So if you curve your finger across the curve C, then you have the thumb pointing to the n hat direction. So n hat basically is perpendicular to the small area enclosed by the small curve C. Okay. Yeah. So n hat is perpendicular to the area enclosed by C. So n hat to give us more of an orientation concept of the curve C. Now at the same time, right, the curve C is a closed curve, then it gives me a small section area, right, delta A. So let's call this is area, right, the actual area enclosed by the C. Now I can define a vector. I can define a delta A vector. So let's call this area vector. Okay, so area vector. So area vector means you have a magnitude, you have a direction. So in this case, my magnitude is simply just the actual area of this small curves, small area enclosed by curve C. Then the direction, I can just use the n hat to represent its direction. And together, that give me this very particular vector called area vector. Okay. So then next, I'm gonna do an operation like this. First, we calculate the total circulation of a vector field around this small curve C. So the vector field is something that I did not draw it here, but it's present in the 3D space around this curve C. So you calculate the total circulation around this curve C. And then you divide it by this area of enclosed by the curve C. Okay, yeah. So this operation right here, using wording, is basically you get total circulation of F around C, then divided by area enclosed by the C. So I just created an expression, right, of fraction, which equal to this, right? Yeah. Now, then often in time, you actually probably have seen this kind of thing quite a lot. You know, you have something divided by an area, okay? So I could also call this as a circulation, okay, per unit area. Okay. So if this area enclosed by curve C is one unit, then this fraction basically gives me a circulation per unit area. Now, also bear in mind, okay, right now, this fraction, right, refer to the circulation around this small area delta A. There's also a direction involved here, okay? So n hat, yeah. Now, apparently, if your n hat is pointing to different direction, then the fraction in here will be different, okay? Yeah. Now, when you see this kind of wording, circulation per unit area, and if you recall to some other previous physical concept, right, or physical definition, for example, mass per unit volume. What does mass per unit volume give it to you? Density, right? Now you have something per unit area. So that should struck you, okay, so that got to be something close to a density concept, right? If you have mass per unit volume, you get a density. So you get now circulation per unit area. So that's also a density concept. So as a matter of fact, so this is can also be called, right, circulation density concept. Now, however, this is not quite a density concept yet, because the delta A density, when you talk about density, is always a very locational concept. At that particular location, you have a density. Okay, you're not really talking about density. What is the density over the whole volume at here, right? Unless it's a uniform density. Okay, so then what we do is we create the density concept by letting this delta A go to 0, right? So now we're taking limit. Okay, so we create a limit concept here now. If delta A goes to 0, then the original small section area delta A becomes a point. Now that's what we want, right? Now you got a density concept. So technically, right? So what we just have created here, so this one, what we have just created, this is called circulation density. So this limit gives you a circulation density concept. So very much like a volume, mass density. If you have a mass over delta V, you let the delta V go to 0, right? You get a mass density. Good. So what is so useful about this expression then? Okay. Now, without a proof, or my lecture notes actually has a proof, okay, that we can show that this limit is actually equal to curl F dot n hat. So this limit can be proved is equal to curl F dot n hat. And remember what del F is, okay? Del F is basically del cross, curl F is del cross F. Okay, that's curl F. okay? So the purpose of introducing this circulation density here is to introduce how this curl F is actually related to this circulation density. Now, if I look at this expression here again, okay, and relating to some of the very basic concepts we have learned. So tell me, if I have a curl F dot n hat, first of all, what is the curl F? Curl F calculation is this formula over here. You get a vector, right? Curl F will give you a vector. And then you're using this vector to do a dot product with a unit vector n hat. And it's resulted with this circulation density, which is a scalar quantity, right? So this is a scalar. Okay. So back to the basic concept. When you use a vector dot a unit vector, physically, what does that give it to you? So you have curl F dot n hat. So that should give you what? Length projection, right? Again, it's the length projection of this vector in which direction? In the n hat direction, right? So if I get back to my drawing edit here, here's your n hat. Then at this particular location, you would be able to draw another vector called curl F, okay? And if you project the curl F into this direction by doing the dot product, then mathematically, what does that give it to you? It gives you the circulation density in the n hat direction, okay? So this is basically circulation density in n hat direction. This is the connection, okay? This is the connection in here. So you got, here you got a curl F calculation mathematically, but you can calculate it. Here you got a location in the vector field, and you can create a n hat in any directions at that moment, right, at that location. Now, if people ask you, what is the circulation density in the n hat direction, then what would you do? You just have to use the curl F dot the n hat to give you the circulation density. Is that good? So here's another illustration, right? So you probably have played the game, okay? If you have pinwheel, okay, and you hold the pinwheel, and you hold the pinwheel in the wind, and you want it to spin as fast as possible. So what would you do? And you must have to orient it to a different direction until it's spinning the fastest, right? Now, if the P at here, or P hat at here represents the orientation of the pinwheel that you're holding it, that's equivalent to the n hat we drawn over here, right? Then as you can clearly see, what direction should you orient this P hat or the n hat so that you can have the fastest spinning of the pinwheel? Correct, exactly. If you orient this n hat to be the same direction as this curl F, then you will get the fastest spinning. Now, of course, there's a certain location you actually don't get any spinning, right? That's when n hat is actually perpendicular to the curl F. Okay, now that's the concept of a so-called circulation density. You have a vector field, you have a location, and you might want to be interested to know how can I get the information of the rotation when I orient it to different direction, right? Not just one single, there are infinite directions, literally, right? Maybe one direction is in particular interest is what direction I get the maximum rotation, and what direction I get the zero rotation. So this is the connection, how you can get the information from here. Okay. But however, you also have to be very clear. Okay. So what calculation this give it to you? This gives a so-called location-wise. Location means one single location, a point, right? That's a point. A point-wise rotational information. Right? Rotational information. So at a location, you have curl F, and curl F has two informations, direction and magnitude. Okay? Direction and magnitude. The direction of this given by the curl F vector give you the direction that you get the maximum rotation. And the magnitude of the curl F will give you the actual speed of the rotation of that location. Okay. Okay. So this is the connection. So next time, if people ask you, so what's the meaning of curl F? And you can see that curl F actually give you, the physical meaning is the rotational information at a certain location within a vector field. Its direction gives me the maximum rotation, however you point into, you get a maximum. The magnitude will give you a speed of rotation. Okay, so let me show you a website here, just to illustrate this a little bit more here. Okay? So let's say in this website you have a vector field given by negative y, x, 0. And if you draw this vector field out, okay, if you look at from the top, right, and that's basically a vector field look like this. So now if you throw a ball into this vector field, and the ball will certainly flow around this z-axis. It's like a river, right? It's being pushed by the river and then rotate around the z-axis. But be careful, this is not the curl. So what is curl then, right? So you look at the ball itself. You look at the ball, right? Focusing not the ball rotating about the z-axis, but focus on the self-rotation of the ball. So the self-rotation of the ball is actually the information given by the curl F. Good? Because that's the moment, right? That's the rotation at that particular location. Okay. So that's why I want you to caution the concept macroscopic rotation versus microscopic rotation. So the microscopic is actually given by the curl F. Okay. It gives you a point information. The macroscopic is more of just generic. You look at the vector field, of course, there's certainly a rotational trend, right? Is going on there. Okay, yeah. So this is an example that the curl is not 0. Basically, there will be self-rotation at that location like this, okay? Now, if you would change to a different vector field, so this time, use this vector field. So to basically become negative y, x, and over x squared plus y squared. So the vector field changed. And by excluding the 0, 0 location. Okay? And this time you throw the ball into it. Okay, so the ball will still feel like you still rotate around the z-axis, right? But however, if you focus on the ball's self-rotation, and guess what? There's no self-rotation anymore. And if you calculate if you calculate del cross F, you actually will get 0. Basically, you get curl F in this case is 0. Okay, so that's the difference, right? If you get often in time, right? Remember what we said at the beginning of the review. If curl F equal to 0, what kind of field is it? If curl F equal to 0, what kind of field is it? Conservative, right? So if you have a conservative field, the curl F is 0, then if you throw a ball into the conservative field, would you expect the ball to do self-rotation? The answer is no, right? So that's the understanding of the curl F and rotational information within certain vector field. Okay, excellent. But I need to caution it here a little bit here because this vector field has over x squared plus y squared. Now we excluded x, y not equal to 0. Now, if this x, y not equal to 0, 0 is not excluded, this is actually not a conservative field. Okay. The reason is because at the beginning I mentioned the vector field needs to be continuous over the region that's described. If your region includes a 0, 0 origin, then it's actually not a conserved field, okay? If you exclude this region, this origin, 0, 0, then you can claim it's a conserved field. Okay, that's a little bit of a tricky concept over there, okay? Yeah. But I think in terms of the interpretation of a curl, right, these are the fundamental, basically, meaning of a curl at here. Okay. In terms of computation, I don't think it's anything too difficult. Basically, you just have to calculate del cross F, and then you would be able to get, right, the curl. Okay. Any questions on the meaning or interpretation of the curl here? It's been a lot of time, on how to better interpret a curl. Just like interpreting of a greeting vector, del apply the greeting operation to a scalar function f. You got a greeting vector, and I have emphasized, out of this course, if there's one thing you need to remember, right, is that the greeting vector pointing to the direction of the greatest increase of the function f. Right? So those are the meanings behind those mathematical operations. Okay, so the next is a theory. Okay, that's also going to help us in terms of vector line integral. It's called the Green's theorem. Okay, so Green theorem. So let's take a look at what Green theorem is all about. So first of all, Green theorem is a theorem for a 2D vector field. For 3D vector field, we actually will have a different theorem. Okay, it's called Stokes theorem at the end. But for now, okay, for 2D vector field, we have this Green theorem. Okay. And let me write down the definition first. So consider a 2D vector field. Let's call this as F. Okay, of course, 2D basic means we're looking at a vector field in XY plane. You can also still draw this in the 3D orientation, that's fine. Okay. So if this is a 2D, then the vector field F is strictly somewhere right inside this plane. Okay. Then apparently, if you calculate this cross product or the curl of this vector field del cross F, because this is 2D, then you can clearly see that you're going to end up with a vector pointing in the z-axis direction. Okay, so that will be the result of this curl calculation. Okay. So now, what I'm interested is, so let's say suppose I have a curve C, okay, inside this XY plane. Okay. And it's closed curve. Okay, so consider a closed curve C, okay, in XY plane. Then what is the vector line integral? Okay, what is the vector line integral over this closed curve C? Okay, so that's basically the initial question. So of course, if you have a question like this, you can certainly follow traditional approach. You say, okay, let's get the parametric equation for the curve C, okay, R of t, and then follow the procedures of a typical vector line integral, and we can get this vector line integral, or the so-called total circulation, right, around this curve C. Okay. Now, however, the Green theorem gave us an alternative approach. And so Green theorem says, so Green's theorem, it says that you don't need to calculate, okay, instead of calculating this vector line integral, okay, it says you could calculate like this. Right? So you can calculate this vector line integral alternatively using this right side expression, which is a double integral. And R at here, so R is the region enclosed by C, okay, by the curve C. And Mn, of course, comes from your vector field, right, which is a 2D vector field F equal to Mn. So you're required to calculate two partial derivative, which give you two functions. Then you calculate the resulted functions integral of this over this region R. And then you get double integral result. And that's equivalent to the result of this vector line integral. That's what basically Green theorem is all about. Okay, yeah. So as you can clearly see, you might want to, so which one is simpler, right? It's hard to say. Sometimes this actually turned out to be much simpler for computation, but sometimes this might be simpler, okay? Yeah. But I want you to, again, interpret this expression a little bit at here, okay? So let's do a little bit of interpretation. Relating to what we have sort of spent a lot of time at majority of this chunk of this lecture here. How do I interpret this Green's theorem, right? So let me redraw this diagram in here. So here's XY plane. And then here is your certain region R, or enclosed by curve C. And the next, before I do this, let's look at the integrand, okay, for this double integral within the Green theorem. So the integrand is partial n over partial x minus partial m over partial y. Now, as you can clearly see, when you calculate this cross product del cross f, okay, and f, okay, equal to mn0, okay, so there's no z component, right? If you calculate this del cross f, according to the formula presented at the beginning of the lecture, and that gives you partial n over partial x, partial m, partial y, and then k hat. Okay, this is the result of the cross product. So the integrand in here, right, is basically the component of this k hat. And that's the curl. So del cross f is the curl. So let's go back to the meaning of curl. Remember what I emphasized. When you calculate the curl of a certain vector field, the curl actually gives you the rotational information at that location, right? Then what does curl dot k hat give it to you? When you use a curl dot a unit vector, what does that give it to you? When you use a curl dot n hat, it gives you circulation density in that direction, right? So then this time, if I use curl dot n hat, what do I get? I get basically the integrand. Then according to my definition, so the results here, this result here, this is the circulation density in what direction? In the k hat direction. It's the same direction as the curl, basically, right? Remember, this is a point information, or this is a location information. Then let's see, if I pick a point within this region, imagine that you have a very, very small circulation, okay, very, very small. So it is so small, it's like around that point. Then what is the circulation density at that location? It's given by this calculation, right? Then what is the circulation density at this location? Again, it's given by this quantity. Does that make sense? So it doesn't matter how many, right? So you pick any points and you can always get a circulation density given by this expression. Now, what this right side expression is doing is you're integrating all of the circulation density within this region R. Integration means mathematically means what? Summation. So you're summing up all of the small circulations or circulation density. You're summing all the circulation densities within this region R, or within the region enclosed by curve C. So what this side is doing in here is basically is that. Then what does it give it to you? It gives you the total circulation around the curve C, right? Does that make sense? If you integrate or if you add up all the mass density within a volume, what do you get? You get a total mass, right? So this is basically exactly the same meaning. If you add up all the small circulation density within a region R enclosed by curve C, then you get the total circulation around this boundary of this region R, or the curve C. That's essentially what Green theorem is telling you, right? Instead of calculating the total circulation, you can calculate integration of circulation density. So over here, it's basically integration of circulation density. And over the other side, you get the total circulation. The connection between the Green theorem to left and right is like that, right? So I'm going to demonstrate a couple of examples in the next lecture, how to properly use Green theorem in the next lecture, right? And as you can see, we have already learned double integral, so the computation-wise, there's no mystery at all, right? Okay, there's nothing new. All right, so I'll see you next week. Right? Now, just a reminder that I posted a formula sheet. I mean, not actually, the other instructor posted already a formula sheet for the final exam. So use it as a reference for your preparation. It covers pretty much all the important formulas, but may not all of this in the lectures. So if there's anything not there, then you can actually Try to write a few times, it'll remember, right? You'll be yours. Okay. Yeah. All right. Any questions? Feel free to come over.